it is very useful to study the frequency response of amplifiers. This enables us to design the amplifiers in such a way that the input signal with a particular bandwidth, that is, range of frequencies, is accommodated in the bandwidth of the amplifier and gets amplified rather than distorted. However, first we must learn how to describe a voltage signal in the time domain in terms of its frequency spectrum. Imagine a sine wave signal shown in this figure, where VA denotes the peak value or amplitude in volts and omega denotes the angular frequency in radians per second. That is, omega equals 2 pi f radians per second, where f is the frequency in hertz and f equals 1 by t hertz, and t is the period in seconds. This sine wave signal is characterized completely by its amplitude, frequency and phase angle theta with respect to an arbitrary reference time. Here the phase angle is 0 as the starting time is the origin. We want to see the different frequencies embedded inside this signal so as to design our amplifier accordingly. For that we employ the Fourier series. Fourier series of a sine wave can be written as this equation on your screen. A frequency spectrum of the sine wave can be drawn using the Fourier coefficient as shown on the bottom right of your screen, and omega naught equals 2 pi over t is called the fundamental frequency. We can see that only one frequency exists as it is a pure sine wave, and the Fourier series is basically the same function. Another example is the square wave signal with the given amplitude and time period. This can be expressed as a sum of infinite sinusoids via a Fourier series as this equation on your screen. Notice that the amplitudes of the harmonics decrease progressively. So we can truncate the series. The frequency spectrum is on the top right of your screen. You can see that the amplitude of the harmonics decrease progressively. So far we have only seen periodic signals. For non-periodic signals such as this, we employ the Fourier transform. Here the frequency spectrum is a continuous function of frequency, as you can see on the top right of your screen, and in general contains all possible frequencies, unlike the Fourier series where we only had discrete frequencies. We can also call this figure a time domain representation of the signal and this figure a frequency domain representation of the same signal.